Hi, the section 10.g, the convexity. So the duration of the bond gives a linear approximation of the bond price when the yield rate changes. So if you calculated the present value at some interest rate, for example, I is equal to 0.03, we can quickly calculate the present value when I changes a little bit, for example, the 0.031. Then change in present value is calculated by the duration, the times the price, times the change in interest rate. So we can calculate quickly. But how accurate this approximation is? So this is just a linear approximation. So if we do the second order approximation, then we can have a better approximation to the bond price. So you have studied the Taylor expansion in Math 2020, the Calculus 2. So we use that idea to have a better approximation. So consider a simple case that the PV of an N-year, the zero coupon bond at I interest rate. So I wrote I%, but just like interest rate of I. So that is equal to 1 plus I to the power negative n. So this is a power function of I. And the exponent is negative n. So the graph of the PV as a function of interest rate I is like this. So it's convex. So if we have some yield rate I, then linear approximation using the duration is like this. So this is the estimated price. So this is the approximated price, approximated the present value by using duration. So basically this always underestimate the situation. Because this function is convex. And of course, the actual bond may be more complicated because we have coupons, but still we have some summation of some cash flow. So we have the convex function, and the approximation always underestimate the price. Yeah, so the bond price when the yield rate changes is actually higher than the linear approximation. So actual price is higher than linear approximation. So this curvature of the PV of I, the present value as a function of I, is referred to as convexity. Yep. So now that we want to define the convexity. So convexity is basically the second derivative of the present value. So the definition of convexity that we write the C sub mod, the modified convexity of I is equal to the second derivative of the present value. Present value is denoted by P of I. So the second derivative, so d square di square of pi, and we normalize this by the price. So that when we calculate we define the duration, that we divide the ddi of pi by pi. So that we do the same thing for the convexity. So this is basically the p double prime of I over P of I, if the prime represent the DDI. Yeah. So, okay, so this is the definition, but how to calculate this when we are given the cash flow? So we calculate this in this way. So at first, remember that the present value. So this is the present value with the yield rate of I is equal to the summation over T of the V to the power T times AT. AT is a cash flow at time T, and the V to the power T, the V is, remember that the 1 plus I inverse. So V to the power T times AT. So to be exact, we may have the index. So we have only finite cash flow. So I is equal to 1 to n of the summation, the V to the power Ti's times the A sub Ti. So what was the P prime of I, the first derivative of P with respect to I? Then, okay, so at first we can see that this is equal to the V to the power T. So V is 1 plus I to the power the negative 1. So that means the 1 plus I to the power T, so negative T times AT. And this is equal to the summation of the e to the power, the negative 1 plus log of 1 plus I times T AT. So to differentiate, always e to the power something is a good form. And we differentiate with respect to I, so that when we differentiate this becomes the log of 1 plus I, maybe the entire amount. So the entire term. So this becomes, okay, so we at first we differentiate with respect to I. So we use the chain rule. So we differentiate this part, the log of 1 plus I. So that becomes 1 over 1 plus I. And we have negative sign, so we put negative sign. Then we do the same thing. So e to the power, the negative log of 1 plus I times T. So, and this is actually the coefficient is negative V. So this becomes the negative V times this one, but this one actually is again the e to the power, V to the power T. Oh, and also the T is constant here. So actually if we differentiate the entire term, so we have T. So then V to the power T, this is the original form. So this is actually the negative, the V to the power T plus 1. And actually also T, we have T. So Vt times this one. So this is the negative T times the V to the power T minus 1, T plus 1. So this means that this derivative is equal to the negative of the summation, the T times the V to the power T plus 1 A sub T. How about second derivative? We differentiate this again. But basically, this is almost the same as the original one. So V to the power T times A sub T becomes V to the power T plus 1 as, times the A sub T. So the T is just a constant with respect to I. So just the T becomes T plus 1. So that means the next time that we have T plus 1 here, and the exponent becomes 1 larger again. So this is T and this is T plus 1. So this becomes T plus 2. Then AT. So now that we have the P double prime of I, so we can calculate the convexity, the modified convexity. So C sub modified of I, the convexity for modified convexity for I is equal to, and this is negative, so positive. So this is equal to the summation of the T times T plus 1 times the V to the power T plus 2 times A sub T. Then the P of I. So P of I, you have the formula here. So that we can derive the convexity, we can calculate the modified convexity by this formula.